Today we're going to talk about something called network flow. And look, this isn't about finding the fastest way to get somewhere. It's about respecting limits. We're going to break down the math that secretly runs everything from your internet connection to the entire global supply chain. Let's get into it.
And that, right there, is the entire game. We live in a world that is defined by its constraints. Every single system, whether it's digital, physical, whatever, it has a breaking point. You simply can't shove an infinite amount of anything through a pipe that's only so big. You run into this every single day. It's the traffic jam on your commute, right? It's that buffering wheel when you're trying to stream a movie. It's the maximum amount of water that can flow through a city's pipes. These aren't just ideas. They're the hard, physical, and digital limits of our world.
So this is the question. This is what network flow algorithms were born to answer. It's not about speed. It's about throughput. It's about figuring out the absolute maximum amount of stuff, whether that's data or cars or packages that can get from point A to point B, given all the limitations along the way.
Okay, so to tackle a problem this big, we need a way to talk about it. We need a formal language, a model. And in computer science, this is called a flow network. Let's take a look at its parts, which are actually pretty simple, but really powerful.
First up, we have nodes. Just think of these as the points, the junctions in your system. A node could be a highway intersection, a router in your home network, or a massive warehouse in a supply chain. They're just the spots where things arrive and then depart from. Next, connecting those nodes, we have edges. These are the pathways, the channels. An edge is the stretch of highway between two intersections or the fiber optic cable connecting two servers. It's the route that things actually move along.
And this is where it gets really important. Every single edge has a capacity. This is its hard limit. It's the absolute max amount of flow that edge can handle, period. A road can only handle so many cars an hour. A cable can only handle so many gigabits per second. This number is totally non-negotiable.
Now, in every flow network, you're going to find two very special nodes. You have the source, which is the starting line, where everything enters the system. Think of it like the main water reservoir for a city. And then you have the sink. That's the finish line, the final destination where everything is either used up or leaves the system.
And this right here is rule number one, the absolute golden rule. The flow going through any edge can never, ever be more than that edge's capacity. But there's a second rule that's just as crucial. Flow is conserved. For any regular node, one that isn't the source or the sink, the total amount of stuff coming in must equal the total amount going out. Nothing gets magically created or lost along the journey. Okay, so we've got our model, we've got our rules, but how do we actually find the system's real true limit? Well, the answer is a little weird. It's not about finding the best, fastest path. It's about finding the absolute worst bottleneck. This is the big question. This is the max flow problem. And notice what we're asking. We're not asking for the shortest path or the cheapest one. We want to know the absolute maximum throughput the entire system can handle at once. It's about finding the best possible outcome for the network as a whole.
And here's the big twist. The solution isn't found by tracing a route from start to finish. It's found by drawing a line, a slice, across the network that completely separates the source from the sink.
We call this a cut. So, the min cut is the specific slice you can make that has the smallest possible total capacity of all the edges it crosses. Think of all the different ways you could cut the network in two. The min cut is the one that goes through the narrowest set of pipes. It is, literally, the system's weakest link. And this leads us to one of the most beautiful and profound ideas in this whole field, the max flow min cut theorem. What it says is that the maximum amount of flow you can possibly push through a network is exactly equal to the capacity of its weakest bottleneck. Your whole system is only as strong as its weakest part. It's the bottlenecks that limit you, not the paths themselves.
So we know the max flow is equal to the min cut. That's great. But how does an algorithm actually find that number? Well, the core idea is pretty intuitive. We're just going to build the flow up piece by piece. Let's see how that works.
This is basically the Fulkerson method. You start by just finding any path from the source to the sink that still has some room. Then you push as much flow as you can, limited by that path's own bottleneck. After that, you update all the capacities to reflect the new flow, and you just repeat. You keep augmenting the flow, path by path, until you literally can't find any more paths with available capacity. Now the catch is, which path you pick matters a lot. Bad choices can make the algorithm really slow. That's why we have smarter algorithms like Edmonds' Karp, which always picks the shortest available path. It proves that a little bit of structure can tame a brute force approach.
This is such a critical insight. For any given network, the final value for the maximum flow, that number, is unique. But the way the flow is actually distributed across the network to get that number, that might not be unique at all. You could have several different configurations, different routes for the flow to take that all add up to the same perfect maximum throughput. And that's a huge deal for things like load balancing internet traffic or planning for redundancy in a power grid.
So let's zoom back out, because this isn't just some abstract problem on a whiteboard. Network flow is the mathematical engine humming away behind so many of the complex systems that make our modern world work.
Seriously, it's everywhere. Internet routers use it to juggle data packets. FedEx and Amazon use it to optimize their entire supply chain. It's used in traffic engineering to manage the flow of cars, in cloud computing to allocate server resources, and even to schedule tasks on a factory floor. If you have resources moving from one place to another under some kind of constraint, you can bet a flow model is involved.
You know, to really get why flow algorithms are so special, let's put them in context. Think about other graph algorithms, shortest path algorithms, like what your GPS uses. They're all about optimizing travel for one person, finding the most efficient route for a single trip.
Or what about spanning tree algorithms? They're all about optimizing the structure itself. They're used to connect every point in a network using the least amount of cable or cost possible. It's about building the most efficient backbone.
But flow algorithms, they play a different game. They could not care less about the shortest path or the cheapest structure. Their one and only job is to optimize the total system throughput while respecting every single one of those capacity limits. They answer the question, how much, not how fast or how cheap.
And that really leaves us with a final, powerful lesson about designing systems. The lesson of network flow is that a truly great system isn't about making every single piece as fast as possible. It's about identifying the real bottlenecks, understanding the system's true capacity, and then making sure the whole network is balanced. It's about understanding and respecting your limits.